In this video, we're going to be looking at a different kind of relative motion problem that involves side wind and side current, and they're about what should the heading be. So what that means is if you want an object to end up directly across, so directly north, for example, of where it started, you would need to head it at an angle relative to the current or the wind in order for it to end up at that location. So here's what I mean. Here I have a few examples. So example 1 is a 200-meter wide river flows due east at a uniform speed of 2 meters per second. A boat with a speed of 8 meters per second relative to the water leaves the south bank and wants to end up directly north. So we want to see in what direction should the boat head, what is the speed of the boat relative to the earth, and how long does it take the boat to cross the river. So let's look at the phrasing of this problem carefully and also visualize it carefully to start out in our solving this problem. So here is our visualization. So the current flows at 2 meters per second east. The river is 200 meters wide. The boat starts here and it wants to end up directly north at this dot. Let's look at this phrase, 8 meters per second relative to the water. So remember, relative to the water means that's how fast the boat can travel in still water. So if there were no current, then the boat would be able to just travel at 8 meters per second at whatever angle. And again, relative to the water, that means if someone were floating in this water, they would see the boat doing this and end up a little bit right around here. What that means is that in contrast to the other types of problems we were solving, the hypotenuse of the triangle this time is the 8 rather than one of the legs of the triangle being 8. So the boat heads something like that. And what we need to realize is that when the boat heads that way, the x component, so the horizontal component of the boat's velocity, we want that horizontal component to cancel out with the current of the water. So this leg of the triangle here has to be 2 meters per second west. And that, again, that's in order for it to cancel out with this 2 meters per second going east. So that's our 8, and that's our 2. And we want to end up finding this angle that I've marked right here. So that 2, you can just transpose it down here. So now we can really easily use trigonometry in order to solve for theta here. So that's what we're going to do for part A. So if you think about your trig functions, that would be adjacent over hypotenuse, so you would want to use cosine. So the cosine of this angle would be equal to 2 over 8. Take the inverse cosine of both sides, and you would end up with an angle of 75.5 degrees north of west. So what that means is that the boat should aim in that direction in order to end up going straight across. Now, someone on the shore will see the boat just go straight across, so let's see what that speed is. So this would be the speed of the river relative to the earth, and then this would be the speed of the boat relative to the river, and then this red one that I just drew in would be the speed of the boat relative to the earth. So we just want to find that leg of the triangle. So the velocity of the boat relative to the earth is, you just use Pythagorean theorem for that, and you would end up doing the square root of 8 squared minus 2 squared, and you would get 7.75 meters per second. And then for the last part of the problem, how long does it take the boat to cross the river? Well, we don't have to worry about any acceleration here. And when there's no acceleration, the speed of something or the velocity of something is just equal to the distance over the time or the displacement over the time. So if we rearrange this and solve for t, then the distance would be the distance across the river, which is 200, and the velocity is what we just found in part B. So you would do 200 divided by 7.75, and you would get 25.81 seconds. Here's example 2, very similar to the one from the previous slide. So we have a boat heading due north, and it can travel at 10 meters per second in still water. However, there is a current of 5 kilometers per hour going east. So in what direction should the boat head if it wants to end up directly north? And what is the speed of the boat relative to the earth? So very similar to the last one. So again, in 10 kilometers per hour, that's in still water. So if there were no current, it would just do 10 kilometers at whatever angle we find. So the hypotenuse of the triangle is going to be 10, and we want this x component, or the western velocity of the boat, to completely cancel out with this eastern river velocity. Then that 5 can be transposed down here, and we want to end up finding angle theta. So again, if you look at it, it's adjacent and hypotenuse, so you want to use the cosine function. So the cosine of theta is equal to 5 over 10, and then you take the inverse cosine of both sides, and you would end up that the angle is 60 degrees north of west. Now we want to find the speed of the boat relative to Earth, so that is this red line that I just drew in here. So it's very similar to part B of the last problem. So remember that 10 is the velocity of the boat relative to the river. That's the direction and the speed in which someone floating in the river would see the boat going. And remember, someone on the shore would just see the boat head directly across. So this 5 is the speed of the boat, the speed of the river relative to Earth, and then the red line is the speed of the boat relative to Earth. So the speed of the boat relative to Earth is going to be the speed of the boat relative to the river squared minus the speed of the river relative to the Earth squared. So we're finding this leg of the triangle just using Pythagorean theorem. So the velocity of the boat relative to the Earth will equal the square root of 10 squared minus 5 squared, and that ends up equaling 8.66 kilometers per hour. One more problem. So a light plane attains an airspeed of 500 kilometers per hour. The pilot sets out for a destination 800 kilometers due north, but discovers that the plane must be headed at a certain angle north of east in order to fly there directly, because there is a wind moving from the east. The plane arrives in 2 hours. We want to find the angle the plane flew at and the wind speed. So here's another one where I have to be careful of the vocabulary. So airspeed means the speed of the plane relative to the air. So if there were someone just floating in the air, that's kind of like the person just floating in the current. That's how fast they would see the plane go. So again, this is how fast the plane could go if there were no wind at all. So it's kind of like the speed relative to the water or the river in the previous problems. This problem is also asking slightly different things, so let's again visualize it carefully. So we know that the wind is moving from the east, which means that the wind is moving to the west. So if you say a wind is moving from the south, that means the wind is moving north. And if you say the wind is moving from the east, that means it's moving to the west. So you gotta really pay close attention to the wording here. So the plane will start somewhere here and wants to end up here, and we know that that distance is 800 kilometers. And we know that the plane will want to head in that sort of direction because it'll want to go a little bit against that side wind. So the velocity of the plane relative to the air, VPA, is equal to 500 kilometers per hour, and that's that hypotenuse of the triangle. And we want to end up finding that angle. So we want to find this angle, and the way we want to do that is we actually know what this leg of the triangle is. And the reason we know that is because we know how long it took to get 800 kilometers, and we know that the distance is 800 kilometers. Remember that when there's no acceleration, the velocity is equal to the distance divided by time. You just plug in 800 over 2 and you get 400 kilometers per hour. So that, the velocity of the plane relative to the Earth, is 400 kilometers per hour. So you can just use trigonometry in order to find that angle. In that case, you would want to use the sine function. The sine of that angle is 400 over 500. Take the inverse sine of both sides, and you would end up with the inverse sine of 400 over 500, and then that angle is a 53.13 degrees. And the angle would be north of east, which you can pretty clearly see from this drawing here. Okay, now for part B, we want to find the wind speed. So remember, this plane is headed in a direction so that the x component of its velocity cancels out with the speed of the wind, which is going west. So this represents the x component of that velocity, which I think I'm just going to get rid of the subscript here. So let's just call it the velocity of the plane in the x direction. So now, since we have these two legs of the triangle, it should be really easy to find this leg of the triangle. So this blue arrow that represents the wind would be going directly opposite to the x component of the plane's velocity. So the velocity of the wind is equal to the velocity of the plane in the x direction. So if we think about it as a triangle using the Pythagorean theorem, we'll have an expression that looks like that. So the velocity of the plane in the x direction will equal the velocity of the plane relative to the air squared minus the velocity of the plane relative to the earth squared, which ends up being 500 squared minus 400 squared. And if you're familiar with your special triangles, hopefully you saw that this is a 3, 4, 5 triangle, so that VPX is just going to be 300 kilometers per hour, and that is the same as the wind speed. So hopefully you get a sense from these problems that if something wants to end up directly in front of where it just has to be at a certain angle. So hopefully you understand a little bit more about how to solve these types of problems.